Hello, I am providing a summary of all the ideas that we've covered up to now in class that will be on our pop quiz on Friday and in the homework for the due on Sunday. Alright, so we started with this plot on Wednesday of our class, and I updated the error that many students pointed out that I had not changed, that the high entropy would have high number of configurations. So this video is about making sure you feel comfortable with generating H versus S curves, connecting them to delta G versus T graphs, and applying them, applying chemical reactions and putting the states in their proper place. All right, so let's start with the summaries that we had in class, which is this is the delta H analysis flowchart. Pretty much start from the top and work our way down. So if there's only one reactant or one product, remember this is what we call the one particle. If there's one particle on either side of the reaction, reactant or product, if that's there, then it automatically has the lowest potential energy due to net bond, either formation, and so we're going to look at chemical reactions from that perspective. 2 is if you have multiple reactants or products, like reactant 1 plus reactant 2 make product 1 plus product 2, and so on. Then what we're asking you is to look for an element, and what we called that was the AA bond, right? BB bond, and if so, then this side will always have the highest potential energy. In this case, but what happens if you have an AA bond on both sides, right? And if you have that on both sides, then we're going to look for ions. Is R2 and P2, are they ions? And if they're not ions, then what we're going to do is look at phase, right? So the very last thing we do is look at phase to see if there's some type of potential energy ranking we can make. Now this is very uncommon in general, but as we go through analyses, if that's the case, then we would make our analysis based on phase. Entropy is based on phase, right? So it's primary analysis or phase. Greatest gas number of particles have the highest entropy. So we call this the primary analysis for entropy. We're just going to be, we're sort of independent of the identity of the gases, we're just counting them up. Secondary analysis is used if you have the same number of gases, right? Same number in the reactants as you do in the products. If you have the same number, then what we're going to be looking at is greatest mass. And so we have examples, and this is what we call the secondary analysis. Okay, so these are the tools that we're using, and now we've practiced them. Okay, so let's start here. So what we're going to do is walk through an analysis that we would expect you to make. Here we have phosphorus combining with, so let's take a look. No, not that. Okay. So what we want to do is be able to assign delta H and delta S so that we can then assign the correct PEC diagram. So the first thing we're doing in the context of energy is looking at the bond strength, and we do that by looking at the types of bonds that are in the reactants and products. When we look at the reactants, we see that we have two elements, phosphorus bonded to itself, chlorine bonded to itself, and in the products, the phosphorus bonded to chlorine. So we have AA bonds in the reactants, AB bonds in the products. Delta H would be assigned this way. Potential energy goes from high to low. AA bonds, and the reason why AA bonds are weaker, higher potential energy, is that they're less polar, giving weaker bonds. AB bonds are more polar, and they're stronger in general. So we would assign delta H this way, going high to low. And if it goes high to low, then the sign of delta must be negative, or less than 0. Okay, so that's the energy analysis. So delta H less than 0. We then look at the entropic analysis. And again, phase is the main consideration. We have a solid, which we pretty much ignore. 6 gases going to 4 gases, high to low. Same trend in terms of delta S, but for different reasons, because it's gas particles, but it's still going from high to low. That means the change here is also negative. Remember, more gas particles means more configurations, less particles means fewer configurations. And since we're going that way, high to low, delta S is negative. So now we've assigned delta H and delta S. And so if we take a look at these PEC diagrams, what we can do is rank each of them in different ways, right? So we can take a look at them and say that we have the reactants going to products, and then we're just keeping track of the change in potential energy. So if we do that, what we see is we have for A is going reactants low, products high. B is going products low, reactants high. C is going reactants low, products high. And then D is going reactants high, products low. So these are the signs associated with delta H for those processes, right? So 2 of them are exothermic, 2 of them are endothermic. And it's really good to kind of feel comfortable with what each one of these PEC diagrams has in relationship to energy. We could do the same thing for delta S. Reactants are low, products are high. In B, products are low, reactants are high. In C, reactants are high, but products are low. In D, reactants are low, but products are high. And so it's really important to, in my opinion, to make sure you can rank where in terms of configuration and entropy, what's changing, how is the change for each one of these diagrams. And now that we've analyzed it this way, since in our reaction analysis we know delta H is negative, delta S is negative, and from that case that makes the answer, choosing the answer, much clearer, that we see an exothermic reaction, and this is the case where the reactants have more gas particles. So delta H negative, delta S negative. And so constructing arguments on how you picked a PEC diagram, what is it about the reaction that leads to your energetic analysis and entropic analysis, is a very good practice. All right, so we had this reaction in class, and we're going to walk through the similar type of analysis here. What is delta H? What is delta S? And so from the potential energy side, we're going to just, again, might have been a little challenging to follow the small changes in the previous slide. So here I'm doing it a little bit bigger so you can see. So just for review, this is the change in potential energy for option A, change in entropy for option A. They're both increasing. In B, they're both decreasing, right? So in entropy, you're going from high to low. Entropy, high to low energy in option B. And in option C and D, they're different, right? And so let's take a look. So first in C, you have an endothermic reaction, so delta H is positive. But entropy is changing as you're going from high reactants to low products. So this is an opposite trend. They have different signs, so delta H is positive, but delta S is negative. When we look at option D, we have an exothermic reaction. And we also have a positive change in entropy as you're going from low entropy reactants to high entropy products. And that would lead us to delta H of negative, but delta S is positive. So these are the four stories, the four characteristics, and what happens when potential energy changes and when entropy changes. So now that we have that established, we can look at our reaction and take a look at delta H. So going down our checklist, we're looking out for one side that might have only one particle, one reactant or product. We see that in the reactants, so that has to be the lowest potential energy. We also see that it has AB bonds and all the others have AA bonds, but our primary analysis here is one particle breaking into two. So we're going from low to high potential energy, delta H is positive. When we do our entropy analysis, we see one gas in the reactants, one gas in the products. We have to go to secondary analysis, and we see the heaviest gas is in the reactants, the lightest gas is in the products. So we go from high entropy to low entropy based on secondary consideration, and that would be delta S is negative. So we have a clear story that we have an endothermic reaction, but entropy is decreasing, going from reactants to products. We can identify that as option C. So option C has the correct trend for H versus S. Okay, so we got to this at the end of Wednesday's class, which is constructing the delta G versus T curve. So there's a couple of examples in this video. The first one is going to be a thorough analysis, so let's take a look at it. So first, what is delta G? Delta G is a function that is composed of three variables: delta H, the temperature, and delta S. And we make graphs of it, so it's a line. We make y versus x graphs. And we want to do where y is delta G and x is the temperature, capital T. So there are four possibilities, because there are four possibilities of signs for delta H and delta S. There are four graphs. But to graph it, what we're going to do is we're going to rearrange it. So we get minus delta S times T, right? So that's our slope. And that gets us into our y-intercept form, which is mx plus b. And so what we're going to do is split the four options, right? And we're eventually going to summarize the options that are there. But first we need to analyze how we would take the delta H and delta S data given, right? So these are going to be these are the four graphs. So what we want to do is say, well, how do we take the delta G versus T data given and decide which of the four graphs we have? All right, so if we do that, we make our graph, delta G versus T. And now the first thing we have to do is assign delta H. So delta H is where delta G is equal to delta G when T equals 0. So what we're going to do is we're going to take the value of delta H and put it along the y-axis. So if it's minus, it's going to be below, it's going to be negative, and if it's positive, it'll be above, but it'll be present right on this axis. So delta G equals delta H. That's the first thing we're going to do. Second thing is to recognize that any value of delta G that's negative is product favored. Any value of delta G that's positive is reactant favored. Okay. So we look for the sign. So delta H is there. It's less than 0. And so we can, at T equals 0, we can put the first point. The first point is here. It's minus 252.7. When delta G equals 0 and temperature equals 0, delta G is minus 252.7. Right? We call that the y-intercept. The y-intercept is delta H. Right, the last item is the slope. So the slope is equal to minus delta S. We see that our value of delta S is minus 410.3. So we have to take the negative of that, and we get positive 410.3. So we get a positive slope, right? Positive slope, because our entropy is negative, our slope is positive. And because we know its value, it is positive 410 joules per Kelvin. Okay, and so we can also find the x-intercept. The x-intercept is going to be critical because this is when delta G changes sign. And when it changes sign, it changes directionality. It can go from product favored to reactant favored. So what we see here is that, and this can be calculated. It's calculated as to be delta H divided by delta S. But we have to keep in mind that delta H and delta S need to be in the same unit. They both need to be in either kilojoules or joules. So I took my delta S and divided by 1,000. That gave me delta S in kilojoules. And if you do that, you see that the value is 616 Kelvin. So any temperature below 616 Kelvin is going to be the product favored. And any temperature above 616 Kelvin will be reactant favored. And we're going to go over that in detail in another problem. But in general, this is kind of all the information we can extract from our problem. And now we can answer which one of these Roman numerals corresponds to our graph. All right, so let's take a look at analyzing the different graphs. So what we see is we're just going to look at the sign of delta H. So if delta G starts off positive, then delta H is positive. If delta G starts off negative, then delta H is negative, right? So that's the key in terms of the relationship between delta, like how do we get delta H from these graphs? Then we look at the slopes here. The slope here is positive. In Roman, so the slope here, if the slope is positive and delta S is minus the slope, then it's minus times a positive value, which is minus, so delta S has to be minus. In Roman numeral 2, the slope is negative, so delta S is a negative of the slope, so that's a negative times a negative, which gives us a positive, so delta S is positive. Here the slope is negative, delta S is negative times a negative, or positive. And then in Roman numeral 4, the slope is positive, which means delta S is a minus times a plus, which is negative. So now we have the four categories. Delta H is greater than 0, delta S is less than 0. And if we use these values to construct these four possibilities, we can now assign the correct answer, which is Roman numeral 4, which we kind of already knew because that was the graph that we constructed. But we can see, hopefully this is a good practice to how do we, when we're given delta H and we're given delta S, or we calculate it, we would use these tools to be able to analyze the problem and select the delta G versus T graph. Right, so what we'll be doing on Friday, or what we did on Friday, is to calculate delta H and delta S of reaction and use that information to calculate delta G of reaction at any given temperature. So let's go through an example where we do that. So how do we obtain delta H of reaction, delta S of reaction, and delta G of reaction at a given, at a given temperature? Okay, sorry, I didn't mean to do that. All right, so the first thing we have to do is calculate the individual delta H and delta S of reaction, right? That's what we're going to do. And we do that by using the table in the data. So delta H is calculated by summing up all the products and subtracting it from the sum of all the reactants. You got to kind of keep everything in the parentheses. You sum everything. You multiply the values in the table by the coefficients that are present, right? That's also key. So let's do that. The first value, we only have one product here. That's alanine. and we get the value of minus 528.4, and we multiply by 1. Now I'm putting the 1s in there just to show you that, yes, we have to use the coefficients. All right, so that's the only product, minus, and now we have to sum up all of the reactants. So we have to go 2 times the delta H, a formation of CO, plus 1 times the delta H of NH3, ammonia, plus 1 times the delta H of H2, which is 0, and we compute that. So my suggestion is to do the parentheses first. So take the minus 528.4, well, that's only one value, but do the 2 times minus 110 plus the minus 45.9, then subtract that from minus 528.4. So if you do that, I get minus 261.5 kilojoules. Let's do delta S. So delta S has the same formula. Once you have the formula, you just sum up the products, delta S, sum up the reactants, delta S. 1, and then the entropy change is 103.5 for alanine, minus, now there's more terms here, so we're going to put a parenthesis, so 2 times 197, that's the entropy of CO, 1 times 192.8, that's the entropy of NH3, and 1 times 130.7, which is the entropy of H2. If you add all that up, it's minus 615.4 joules per Kelvin. So now we can use delta H and delta S to calculate delta G at any temperature using this formula. So we're going to ask, what temperature are we running at? So the values given in this table of delta G are only good at 298. We never ask you to calculate at 298. So the values here aren't useful to us. So what we're going to do is we're going to calculate, this is only good at 298, so what we're going to do is calculate at 100 degrees Celsius for practice, or 373 Kelvin. So this is done in 3 steps. Step 1, you have to have delta H and delta S of reaction in the same energy unit. One's in joules and one's in kilojoules. Usually we report delta G in kilojoules, so the most straightforward way is to just take your delta S and divide by 1,000, right? And that gives you kilojoules. So here our delta S is minus 0.615 kilojoules per Kelvin. Step 2 is to take delta G. We're going to calculate delta G at 373. Remember, delta G is temperature dependent. You have to calculate it at each temperature. So in this case, we're asked to calculate it at 373. So we take our delta H minus T, 373, times delta S. Calculate that, and we get minus 31.6 kilojoules, or product favored. So we know delta G, it's product favored. Step 3, well, this is optional, but what we're going to do is check, is this product favored? Should this be product favored? So when we plot delta G versus T, we see that we are below a certain temperature. We should be product favored. That special temperature we calculate as delta H divided by delta S, and that's 424 Kelvin. Okay, so it's 424 Kelvin. We're only at 373. We're lower than it. So yes, we expect delta G to be less than 0 at any temperature below 424. We are below 424, so the answer, so we're checking and we're saying yes, we expect this kind of behavior. And this is helpful when you are want to check your, especially during an exam, you want to make sure your number makes sense. Okay, so we did this on Wednesday, which is introduce the concentration versus time. Concentration versus time is shown here, and it is the equilibrium concentrations, right, that occur when there's no change over time. So there's no change over time. What we see is that there's more B than A as time kind of goes out to infinity. What does that mean? That means the reaction is product favored, And what we want to know is which one of these PEC diagrams is consistent with product favored behavior at high temperatures. Okay, so if we do that, we can analyze each one of these graphs, and we can see for options A and B, A is product favored at high temperatures because the products are in the upper right. B is product favored at low temperatures because products are in the bottom left. Options C and D are the always never case, and C, it's never product favored because it's in the upper left. And D, always product favored. So what we saw was in both cases, product favored behavior, only at high temperatures for option A, but always favored at high or low temperatures. So we had two different answers for this analysis. Product favored at okay, and then for the H versus S curve, let's make sure that we designate the four regions of favorability so that the never always is on the negative diagonal, and then the positive diagonal has the favorability in the upper right. It's favored at high temperatures, the state that's in that box, in that region, and then favored at low temperatures. Okay, so what I'd like to do, I know we did this problem, at least numerically, so let's bring up the numbers here for delta S. And so what we want to do is to provide some more details in how you construct a quantitative delta G versus T curve. So we have delta H, it's minus 261 kilojoules per mole. Delta S is minus 615. So I think I fix it soon. So the first thing we do is we put delta H along the y-axis. So delta G equals delta H on this axis. And so we get minus 261. We go where delta G is negative, and we put minus 261. Let's keep in mind that any delta G value that's negative, so if you're below in the line, the x-axis, it's product favored. If you're above it, reactant favored. The slope is minus delta S. Okay, so there, I put the minus sign, so it's minus 615 joules per Kelvin and minus 261. All right, and the first thing I'm going to do is take the slope and sort of convert it into kilojoules, and then take the negative of it to give a positive slope. So we start with the point minus 261. We draw a positive slope. And the slope, the quantitative value for the slope is positive 0.615. The x-intercept, where we cross the x-axis, the temperature axis, that's the critical temperature, which is equal to delta H divided by delta S. If both values are in kilojoules, then we can divide them, and we get the critical temperature is 424 Kelvin. So let's make sure it's clear why this is a critical temperature. It just means now that low temperatures, what low temperatures means in the context of this reaction is any temperature below 424. High temperature is any temperature above 424. And what we see is any temperature, delta G is going to lie along this line, and all of those values are delta G is negative, right? So all those temperatures lead to negative delta G values or product favored. Any temperature above 424 leads to delta G values that are positive and therefore reactant favored. Okay, so in terms of the analysis, what we're going to ask you to do with delta G versus T is either qualitative or quantitative. If it's quantitative, we expect you to be able to make this analysis looking at delta H along the y-axis, the intercept, x-intercept by dividing delta H divided by delta S, and then making the correct slope. Okay, so the remainder of this video involves the most often missed questions on exam 1A or the quiz. So we did this one in class, and let's just talk about it. So this question is about identifying that there are AA bonds and ionic bonds in the reactants, ionic bonds and AA bonds in the products. So that leads to using the tertiary, right, energy, which is, okay, we have weak bonds on both sides, but we have ionic substances. So we look at ionic substances here. What kind of ionics? We have the +1s, ammoniums, and we have the +3 aluminums. So what we know is that the +3s times, they're going to have a -6 potential energy, aluminum oxide, +3 times -2. They're very strong interactions. The +1 for NH4 plus are weaker, and so we have an exothermic behavior based on ionics. We could, okay, so that would be our analysis based on ionic strength. To assign entropy, that's much clearer because there are no gas particles in the reactants, but 15 gases in the products. So delta S is definitely positive. The H versus S curve here, well, we know the reaction is exothermic, so I put the R has to be at high potential energy, products have to be at low. And now we have to make sure that the products are drawn at the high entropy part, so we put the products there, and the reactants would correspondingly be there. So that would be the H versus S curve, and I did that just for practice, but we have to keep in mind that in this problem, there's only two possible answers, B and C, and that's because this question's asking about reaction path, not the configurations. And so since we've assigned it as exothermic, the answer would be B. Okay, so this question was answered only 30%, and so let's talk about what we meant for this problem. So we're supposed to be arranging this problem based on the weakest bond to strongest bonds present. Weakest bonds have the highest potential energy, they're the least polar, and they're longer. So when we do the ranking, it looks this way, right? HF is the shortest bond, the lowest potential energy, most polar bond. Fluorine is the most polar atom, is the highest electronegativity. But it's also the smallest, so it's the shortest bond. And so when we look at selenium on the periodic table, it goes oxygen on the row 2, sulfur, then selenium. They're all in the same column. So selenium's the biggest, then sulfur, then oxygen, right? So oxygen is the smallest. So we have that column, and so when we go to ranking bonding, the H selenium is going to be the weakest bond, then H sulfur, and then H oxygen. This is just the general trend of polarity. And then when we're going across a row, fluorine is smaller than oxygen and more electronegative, so that would be stronger, right? So fluorine is the smallest element on this list, and we know that from the periodic trend data. So electronegativity tracks with size. So the smaller the atom is, the more electronegative is. The smaller the atom is, the stronger the bonds it's going to form. Right, so here we have some questions, and we're asked which one is endothermic. So let's look at our recipe for endothermic. The recipe for endothermic is that the products have to have weaker bonds, right? Weaker bonds, meaning they'll have AA bonds, and reactants have AB bonds or stronger ones. Also, a recipe for endothermic behavior is if the reactants have one particle. If there's one particle in the reactants. That means it's got to have the lowest potential energy. It has the additional bond, and that would mean so when we look at our reactions, option A, or the first option, has a AA bond or something bonded to itself. Everything else is polar, so it would be stronger. The first option would be predicted to be endothermic. In the second option, we see the second case, which is we have one particle, A2CB3. It's one particle, and it's breaking apart into two. And by breaking apart into two, it's losing a bond. That net loss of a bond leads to endothermic behavior. And then option C and D are incorrect because you either have one particle breaking or two particles making one. So now the most stable, in option C, the most stable side of the reaction is the products. And in D, the AA bonds are reactive, and that would be the exothermic. Okay, so this question might have thrown people off. So what we're looking at are molecules that only contain CH bonds for the most part, CH and CC. And so the ranking here was just based on the total number of bonds. So the more bonds you have bonded together, the more stable the overall molecule is. So what we're doing is we're just ranking, okay, so C2H6, it has the least potential energy. It only has, when you draw it out, it only has like 7 bonds. While C6H14, clearly there's many more bonds associated with it. It has the most polar bonds, or the most bonds in general, and that's going to have the lowest potential energy or most stable. So the option here would be having C6H14 be the lowest potential energy. They all have the same phase, so we're just really just counting up the number of bonds. All right, so the final example we have is ionic. So you were asked to rank lower and higher potential energy. So the first thing we do is we do our charge analysis. So for FeO, we have we have O2 minus, and to determine iron's oxidation state, we sum the charges and set it equal to 0, which is the total charge of the ionic substance. And that means iron has a 2+ charge. We do it for iron carbonate. Carbonate also has a -2 charge. This is from your polyatomic ions. That the 6 that you have to be able to recognize, carbonate, those are listed in our reading. So it's the same argument. Iron plus 2- has to equal 0 here, and it's also 2+. Titanium, so O is 2-, so titanium plus 2 times a -2 has to equal 0. Solving for titanium, it's +4. Okay, so with that analysis, we can now, with the oxidation state analysis, charge analysis, we can now rank the potential energies. We have a -4 potential energy and a -8. That is multiplying the two charges, -2 times +2. If we do that, FeO and FeCO3 have the same potential energy of -4. That's a primary analysis. And then we're going to rank them on secondary analysis based on size. The bigger the ions are, the higher the potential energy, the least stable they are. The smaller they are, the lower the potential energy. So we rank them that way. There's only one -8, that's titanium oxide, so that's definitely the lowest potential energy. And then we see FeO, the O only has 1 atom, but CO3 has 4 atoms, so it's definitely much bigger. Carbonate is much bigger, and expecting to be the highest potential energy. So titanium is the lowest, and the titanium oxide is the TiO2 is the lowest, and FeCO3 is the highest. Okay, well, good luck. These are all the ideas that will be on the pop quiz and homework for the homework for Sunday, the pop quiz that's on Friday, and if If you have any questions, you can post on Discord or come to office hours.